Welcome to S1 Independent Learning, Lesson 1. So starting off with GCSE Essential Knowledge. Please make sure before you go through this film, make sure you've got a print out of the presentation slides so you can make some notes and annotate it as you go along. Or you can just refer back to the video if you choose. And please make sure that you've got pen, paper and calculator, because this isn't a passive video. This is something for you to take part in, and there are examples for you to try during the process of the video. Okay, so today's lesson is going to be looking at all the knowledge from GCSE. We're going to start to take some of the keywords and theory that you've learnt at GCSE and start to put them into A-level context, A-level notation. Just recap and make sure that you know all the essential knowledge from GCSE. So, some keywords to understand. Probability deals with the outcomes of experiments or trials. Okay, an outcome is just a result. So for example, when you roll a dice, an outcome is what you've rolled. An experiment or a trial is actually the process of rolling the dice. Now, several outcomes can be considered together as a single event. So sticking with the dice example, if we roll a six-sided dice, the event of rolling an even number is several outcomes. The outcomes rolling a 2, rolling a 4 and rolling a 6. The probability of these events or outcomes is the proportion of the time that an event is likely to happen, and we usually represent this using either a fraction, a decimal or a percentage. So again, making sure that we understand all the terms that are required. A random experiment is one in which an outcome is unpredictable and is such that repeated trials may give different outcomes. Again, going back to our dice example, that is a random experiment. A set of all the possible outcomes is called the sample space E. So, for example, the sample space when we roll a single dice is 1, 2, 3, 4, 5 and 6 because they are all the outcomes that can occur. In this example, the outcome probability of all these outcomes is equal if it is a fair dice. Notation. Notation is probably one of the most important areas of statistics sometimes and one of the most neglected areas of statistics. Quite often people choose to just write down probabilities, random numbers across a page as answers, etc. and they neglect to include the notation, this kind of P brackets with some sort of description of the event that's occurring inside the brackets. So PA is the probability of the event A occurring. PH could be the probability of a head occurring. PHH, probability of a head followed by a head occurring. P6, probability of a 6 occurring. One that occurs to me now, P rain, could be the probability that it rains on a certain day. Okay, so it's really important because we will be using certain notation to describe events, and then we need to use different notation to describe when we are going to give the probability of that event. Okay, so if an experiment has an a number of equally likely outcomes, the probability of each outcome is 1 over the number of outcomes. So thinking back to rolling a six-sided dice, we had 6 sides, and so the probability for them was equally likely in occurring. So if we had probability of any particular number, let's say 6 for example, everyone wants to roll a 6, that would be 1/6 because there is 1/6 because it's shared equally the 6 outcomes that are on a dice. Generally speaking, this bottom one, this is our important one. This is our true definition of probability. Okay, so the probability of any event is the number of favourable outcomes divided by the number of possible outcomes. Okay, and this is shorthand notation, number of ways to get A. So n brackets A just means the number of whatever's in the side. So this is number of all possible outcomes. Okay, so just a little bit of A-level notation there to get you used to in it. Okay, now experimental probability is slightly different. It's very similar. It doesn't really come up too much in S1, in all honesty, but it's just making sure we cover everything from GCSE. So as it says at the top, if the situation is more complex, we need to collect data to find the necessary proportions. Now, best example that we can give for this is that if you consider tossing a drawing pin in the air 30 times, we could find the proportion of times it lands pin up. Okay, now when if you think about a drawing pin, it's an odd shape, it's not like flipping a coin or rolling a dice, so there's no logical way to actually say what the probability is. So what we do is we have to do it using trials. So this on the top of our probability for the estimated probability is number of times the pin lands pin up. Okay, so U for up. And this is number of trials. Okay. So it is very similar in terms of we're writing it as a proportion, and it's fairly simple to be honest in terms of the fact that we just do the experiment 30, 40, 50 times, and then we can just record it as a proportion of times that it actually landed pin up. This is the important one, as I highlighted earlier. In general, the probability of anything happening is the number of times that that outcome that you expect you're wanting can happen over the total number of events. Certainty. We have to be really sure for certainty. If an event is certain, the number of ways the event can occur, so NA, is the same as the total number of possible events, so NE. And that's why we have a probability of 1 for events that are going to be certain. So sticking with this example of rolling a dice, if I said what's the probability of rolling less than a 7, well that means rolling a 1, 2, 3, 4, 5 or 6. So 6 ways, and it's 6 over 6, which gives us 1. Impossibility is the complete opposite. For impossible events, the number of ways the event can occur, NA, is 0. So what we end up with is 0 over your number of total events, and that gives us 0. So for example, again, rolling a dice, what's the probability of rolling a 10? You can't roll a 10 on a 6-sided dice, so there's 0 ways that this can occur, so we get 0 over 6, which is 0. So that means for all events, the number of ways the event can occur, NA, is less than the total number of events, but it is always positive. And this bit here at the bottom is really important. Okay, probabilities must always lie between 0 and 1. They can be equal to 0, they can be equal to 1, but they must be in that range. Anything else must be an error. Okay, so that means whenever you're working, if you get any other value outside of this range, then you must check your working because it means that you've done something wrong somewhere. Okay, if an experiment is repeated a certain amount of times, so let's say n times, then the number of times an event can occur, so an event A can be expected to occur, is the probability of that event times the number of ways we roll a dice. So if I say roll a dice 20 times, actually let's say 30 times, expectation of a 6 would be given as the probability of a 6, which is 1 over 6, times the 30 times I roll the dice. So if I roll a dice 30 times, I'd expect a 6 5 times. Okay, so quite a lot of theory there. We'll get into some practical stuff now. Sample space diagrams. Sample space diagrams are really useful. They're really important in probability, and actually they're quite neglected in S1. You do occasionally get questions in S1 based around sample space diagrams. There's usually one question on the paper which just involves some sort of probability theory that you'll have to work your way around in order to solve the problem, and it can often link back to GCSE material. So a sample space diagram, when an experiment involves two separate actions, the sample space diagram is useful to list the sample space. So perhaps that involves rolling two dice, flipping two coins, flipping a dice and a coin, flipping spinning a spinner and rolling a dice, all sorts of different combinations of things. But we're talking about combining two separate experiments together and listing their outcomes as a combination. And that's when we need a sample space diagram. Now, sample space diagram sounds incredibly technical, but really it's just a table constructed by listing the outcomes of each action to form row and column headers, and then the contents in the middle of the table are then the combination of the outcomes in the corresponding row and column. So let's have a look at our first example then. So I've got two fair dice are rolled and their scores are added. We want to draw a sample space diagram for this experiment, and we want to find the probability that the score is greater than 7. So what we're going to do is just in the top of my corner, I'm just going to put plus because I'm adding the dice. Across the top, it doesn't matter which way round you do it, I'm going to put dice 1. So for dice 1, I can roll 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 6. We then have dice 2. And on dice 2, again, I can roll 1, 2, 3, 4, 5, and 6. And then I fill in the middle just by adding together what's in the row and what's in the column. So in this position here, I've got 1 plus 1, which equals 2. In this one, I've got 1 plus 2, which equals 3. Now, I'm not going to write this for every one, because what you'll see is it becomes a simple pattern. As we go across, it increases by 1. And actually what I tend to do is a row and then a column, because this top row will match this first column. So 2, sorry, that's not 2, so 3, 4, 5, 6, 7. So going across, 2 plus 2 is 4, increasing by 1 each time. And it's a fairly simple table. Okay, it's a little bit laborious filling it in, it takes a little bit of time. If you take care, it shouldn't be particularly difficult. It's just a way of organising and making sure that we acknowledge every possible outcome that can happen when we roll these dice. Okay, it's organised, it's logical, it makes the whole process simple. Where am I missing? Sorry, let's just go back a second. Just this last little bit of a mistake. Apologies for that. So we should have there a 10, just rushing and not concentrating, 11, 12. Okay. Now, what we're asked in this question is to find the probability of greater than that the score is greater than a 7. So score greater than 7. And the importance of these sample space diagrams is quite often people consider, okay, I'm going to roll a dice. What scores can I get? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11, 12. And then what they do is they say, okay, what's the probability of rolling greater than a 7? It's 5 out of 12. Well, as we can see here, if I roll 2 dice, there's not actually 12 actually it's 5 out of 11 up across the top. There's not actually 12 outcomes. There's 6 times 6, so there's 36 possible different outcomes. Now, looking in my table, I want to find the scores which are greater than 7. So I can just highlight, and I can do this on this table because I'm just being asked one question. I'm looking at all of these values here in this corner. So actually, just counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So what is the probability of scoring greater than 7? It's 15 out of 36. And of course, we can cancel down this fraction, can divide top and bottom by 3, so I get 5 out of 12. Okay, very, very close to the 5 out of 11 that I said at the top, but it is a different probability. Okay then. So this is an example for you to try. So at this point, what I want you to do is read the question carefully. So let's go through the question. A regular tetrahedron has one of the numbers 1, 2, 3, 4 on each face. This is rolled with an ordinary 6-sided dice. The score is the sum of the numbers showing. Draw the sample space diagram and find the probability of event A, which is a total of 9, and event B, which is a total less than 6. So at this point, I want you to pause the recording and I want you to try this for yourself before moving on, when I will do the solution and you can then mark your answer. So if you press pause now. Okay, welcome back. Let's have a look at the solution. So again, we're looking at a table. This time it is important which way round I put it, just simply because I've got the table drawn, but I could have 4 rows and 6 columns instead. So across the top I've got my 4-sided dice, which of course I can roll 1, 2, 3 and 4. Down the side I've got my 6-sided dice. So very similar to what we did a moment ago, just filling in the middle. So 3, 4, 5, 6, 7, 4, 5, 6, 5, 6, 7, 8, 6, 7, 7, 8, 9. See, I'm not even looking at numbers, I'm just using the patterns to work through the table. Now the probability of event A equals the probability that the total is 9. So I've got 1, 2 out of a total of 4 times 6, because there's 4 columns and 6 rows. So I've got a total of 2 out of 24. And you can cancel this to 1/12. We then want to find the probability of event B, so I'll do this using a blue pen to distinguish between what squares I'm looking at. So probability of B is probability is less than 6, so I'm looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of the total events, which is 24. And again, I can cancel this. This is then 5/12. Okay, I hope you managed to get that answer and that you now understand sample space diagrams. Moving on, we have a slightly different type of sample space diagram, which is called a two-way table. And two-way tables can be used to organise responses from set groups of people from 2 separate questions. Okay, quite a common GCSE question. Quite often they're used kind of like Sudoku puzzles, where you have to complete areas of the two-way table, and you'll see that in a moment. So let's have a look at an example. In this example, we've got a total of 50 students. They are asked which drink they prefer, Pepsi or Coke, and then which chocolate they prefer, Milky Ways or Snickers. Now, it was found that 31 students prefer Coke, 28 students prefer Milky Ways, and 10 students prefer Pepsi and Milky Ways. We want to find the probability that the student chosen at random prefers Pepsi and Snickers. Okay, well, if we go over a page, and I've already got a table set up. So what happens in here is a two-way table. Down one side of the table, we are going to put 2 of the outcomes. So let's do down the left-hand side the drinks, which was Coke and Pepsi. The very bottom row we're going to use to do as a total in a moment. Across the top, we're going to put Snickers and Milky Ways. And the last column is going to be a total again. Now, what I know is the total number of students is 50, so that's going to go in this bottom left corner, because that's going to be the total of the number of people who like Coke and Pepsi, and the total of the number of people who like Snickers and Milky Ways. Okay. Now, other information that we are given in this question was that we was 31 people liked Coke, so that is just 31 people in total like Coke. We are also told that 28 people like Milky Ways. So I'll put 28 down there. One other bit of information was that we was told 10 people like Pepsi and Snickers. So I can put 10 people in the Pepsi and Snickers column. Okay, so I'm going to do the answers in a different colour, this part. So you get some marks for getting this far. Now it becomes like a Sudoku because you have to fill in the rest of the table. And what you have to remember is all the rows and columns all add up. Okay, because we've got these totals at the end. So for example, 31 plus something is going to give me 50. So if I do 50 take away the 31, gives me an answer of 19 in this box here. And all you can do is you just answer one question at a time, filling one gap at a time, and as you fill in more gaps, it allows you to fill in other gaps. So, for example, I can now fill in this Pepsi and Milky Ways one, because what I want to do is find what do I add to a 10 to get 19. So 19 minus 10 gives me 9. Okay, so looking across the bottom, something plus 28 will give me 50. So 50, take away the 28, will give me 22. Something plus 10 will give me 22. So let's do 22, take away 10, which equals 12. And then we're almost there. I've almost completed the table. And what we can do is find this last Milky Ways one. So let's just do 12 plus something gives me 31. So we're going to do 31, take away 12, which gives me 19. And so at this point, all I want to do is just double check have I done this correctly. So I'm just going to check this Milky Ways column. Does it add up? 19 plus 9 is 28, and I can just put a little double tick there. So you can see all the rows and columns now add up. And I've organised all that data so I know exactly who likes what. Now in the question, it asks the probability of who likes... let's just go back and check. Sorry, I noted that down. So what is the probability that the student chosen at random prefers Pepsi and Snickers? So probability, I'm just going to use initials, Pepsi and Snickers equals, well, if I look into my table, here you go, this is the number of people who like Pepsi and Snickers. So there's 10 people who like the Pepsi and Snickers out of a total of 50 people. So that gives me 1/5. Okay, so it's just a different type of sample space diagram to organise information given to you in a slightly different way. So here's another one for you to try. So let's go through the question. 60 students are asked which modern languages they study at school, French or German. 35 of the students are boys, 40 students study French, and 19 girls study French. Find the probability that a student chosen at random is a boy that studies German. Okay, so at this point you should pause the video and draw a two-way table to answer the question. Okay, so let's have a look at the answer then. So again, two-way table. Doesn't matter which way round we do this. So let's just write boys and girls. So that was one way that the information was separated. And then we also had that they studied French and German. Mustn't forget my totals column because that enables us to answer this question. We were told that there were a total of, double check this, 60 students, so I can fill in the total down the bottom there. I know that there are 35 boys, 40 studied French, and that 19 girls study French. So again, you can just work through slowly, totaling up using the row totals. So let's do a different colour so for the working. So first of all, total number of people studying German. It's the difference between 60 and 40. So I get an answer of 20. Total number of girls is the difference between 60 and 35. So we're going to get an answer of 25. Okay, so the number of boys studying German is the difference between 25 and 19. So we're going to get an answer of 6. Working down the French column, the number of boys studying French is the difference between 40 and 19. So that gives me an answer of 21. And then let's work down the column again. The number of boys studying German is the difference between 20 and 6. So that we get 14 boys study German. And let's just check across the top to make sure 21 plus 14 equals 35. That is correct. So it looks like we've done this table correct. Now the question asked, what is the probability that it is a boy studying German? So we just use the table to read off where is the boy studying, how many boys study German. So there are 14 boys that study German. The last one we worked out, and so I get a probability of 14 out of a total of 60 students, which can be cancelled by dividing top and bottom by 2 to give 77 over 30. Okay, hope that all made sense and that you understand now how to use two-way tables. So we're now going to look at a couple of types of events. We're going to go into these in more detail with S1 anyway, but it's just to get used to the vocabulary, just introduce it briefly. Mutually exclusive are events that can't happen at the same time. So when we flip a coin, for example, the outcomes and heads and tails are mutually exclusive because they both can't happen at the same time. Okay. Now, if the event A and the event B are mutually exclusive, then the probability of A and B is the probability of A plus B, probability of B. Okay. This is what we call, and is quite often taught in GCSE, as the OR rule. Now, you might not necessarily have been taught the terminology mutually exclusive events, but what we need to just remember at this point is the OR rule. Okay, so if one event happens or another event happens, then we can add those probabilities together. Independent events. Independent events are events where the outcome of one event doesn't affect another probability of another outcome of an event. So for example, if rolling a 6 on a 6-sided dice and flipping a tail on a coin are independent. The fact that I've rolled a 6 on one dice doesn't change the probability that I get a tail on a coin, or the fact that I flip a tail on a coin doesn't affect the probability of rolling a 6. Now, if you want the probability of A and B when they are independent, then we multiply together those probabilities. And this is what we call the AND rule. Okay, so again, should have been taught this in GCSE. We're going to look at this more formally in S1 and look at the conditions as to when we can actually use these. In GCSE, actually all events are manipulated so that you're always dealing with mutually exclusive events and you're always dealing with independent events. So you can always apply these rules, i.e. the and the or rule. Okay, so let's look at how we use these. And where we use these quite often is in tree diagrams. And tree diagrams will form an important part of your S1 study because it will be a whole question on the exam paper, generally worth about 6-7 marks, so coming up to close to about 10%. Okay, so it's important we revise the GCSE use of tree diagrams, because if we can do the GCSE tree diagrams, then actually it gives us a massive head start on what we need to do in S1. So what do we need to know about tree diagrams? Well, they're a type of sample space diagram. The tree diagrams are used to represent the outcomes in successive events. So say rolling one dice followed by another dice, or anything else that you can think of. Each branch of a tree diagram is mutually exclusive, and each tier of the tree diagram represents independent events. And I'll explain that in a second a little bit more to you once we've actually start to construct a tree diagram. So let's look at a standard GCSE type example. We've got a bag, it contains 7 red balls and 3 blue balls. A ball is taken from the bag and then replaced. This is an important part of the question. It is then replaced. We will look at what happens when we don't replace it after these examples. So a second ball is then taken from the bag. So we want to find the probability of taking 2 balls of the same colour and probability of taking at least 1 blue ball. Okay, so here's our tree diagram. I've already got some of the tree diagram drawn for us. So basically, a tier, if you imagine doing a dotted line, let's do a small dotted line. Let's do it in yellow so it doesn't really interfere too much. If you imagine a dotted line down the middle, this is our first tier on the left-hand side. That represents our first event, picking out our first ball. And it helps if you actually kind of think of this and label the tiers of the tree diagrams to help organise yourself when you do these questions. So on the right hand side we have the second tier events. So this is ball 2. Okay, now when I pick ball 1, there are 2 things that can happen. I can get a red or I can get a blue. Okay, these red and this blue, they are mutually exclusive. I cannot pick a red and a blue at the same time. So the branches, these are the branches on my tree diagram, they are mutually exclusive. The independent events are these tiers, and that's the fact that just because I've picked a red ball here, it doesn't affect whether I'm going to put the probability of whether I'm going to pick a red or a blue ball here. The fact that I've picked a blue ball here is not going to affect the probability of whether I'm going to pick a red or a blue here. So I can finish labelling my diagram. It's a different type of sample space diagram because what it does is it kind of maps out the different events that you can have. So here, this is the probability of getting a red and a red. Here, this is the probability of getting a red and a blue. Here, this is a probability of a blue and a red. And here is a probability of a blue and a blue. So it's a different way of mapping out the way what can happen in a set of combination of experiments. Now on each one of these branches I want to label the probabilities. What we was told in the question was that there were 7 red and 3 blue balls. So probability of a red equals 7 out of 10. Probability of a blue equals 3 over 10. Now, these are independent events. When I put that ball back, it doesn't matter what colour ball I picked at the beginning because they're independent. So the probability of a red here is still 7 over 10. Probability of a blue is still 3 out of 10. And this is the same for all these branches in this example. So red equals 7 over 10, and then probability of blue equals 3 over 10. Okay, so we've drawn and labelled our tree diagram. All that remains is to find these n probabilities. Now, because I'm saying the probability of a red and a blue, and rule, probability of A and B equals probability of A times probability of B. Okay, so to find these end branch probabilities, what I'm going to do is I'm going to multiply it across the branches. So I get 7 over 10 times 7 over 10. I'm only going to write it out for the first one. Okay, I get 49 out of 100. I'm not going to cancel it, and you'll see why in a moment. So for the rest of them, 7 over 10 times 3 over 10 is going to give me 21 over 100. 3 over 10 times 7 over 10 will give me 21 over 100. And then 3 over 10 times 3 over 10 gives me 9 over 100. One of the reasons that I don't want to add them all up is, cancel any fractions is because actually I may have to add these fractions afterwards. And actually what you should do is just double check to make sure that all of these probabilities add up to 1, and that should indicate you've done the tree diagram correctly. So 49 plus 21 is 70. 70 plus 21 is 91. 21 plus 9 is 100, so I've got 100 over 100, so it appears that I've done this question correct. This is the tree diagram done fully. Now when you do a tree diagram, if you always label all the branches, always do all the end probabilities, you're actually going to get most of the marks in a question. Okay? You may have to use the information from the tree diagram, but if you get in the habit of just constructing the tree diagram and doing the end probabilities every time, yeah, sometimes it's a little bit of extra work. Yes, we don't necessarily want to do extra work, but every time you do a tree diagram, the process is going to be the same. So this will become really, really easy. Okay, so just keep on doing it every time, label all the branches, get all the end probabilities. You get most of the marks in an exam question through doing that. And then you get the last couple of marks from answering specifically the question, but you get working marks for this whole tree diagram. And this bit here will never change. So actually constructing all the tree diagrams will never change, and so you can get the marks from just doing something that's always the same. In the question, it asks to find a probability of 2 the same. So let's have a look. Probability 2 same. Well, there's two ways we can have this. This is a probability of a red and a red, or a blue and a blue. So going back to our OR rule, probability of A or B is equal to the probability of A plus the probability of B. So this becomes probability of red is 49 over 100. And probability of blue is 9 over 100. And this is where it helps not to cancel the fractions. 49 plus 9 is 58 over 100. This can be rewritten if you want to as 29 over 50. Okay, so then probability at least one blue. Okay, so what are the ways that we can get at least one blue? Well, I could get a blue and a red. So this is probability of red and a blue is better there, I think. Probability of a red and a blue, that's one blue. Probability of a blue and a red, so that's or probability of blue, red, because there's at least one blue there, or the probability of a blue and a blue. So again, using the OR rule, what we're going to do is we're just going to total up all the possible outcomes which match up to what we require. So then I get 21 over 100 plus 21 over 100 plus 9 over 100, which comes out as a total of 21 plus 21 is 42, plus 9, 51 over 100. And that is as simple as we can get it. Okay, so now for one for you to try. Alice is playing darts. The probability she hits the bullseye with a dart is 0.1. Alice throws 2 darts in succession. Find the probability that Alice hits the bullseye just once. So what I want you to do is draw a tree diagram, find this probability. I want you to now pause the recording and attempt the question before we proceed. Okay, so let's have a look at the answer then. Probability of hitting a bullseye, so we're going to have H and M for hit and miss. We're going to have dart 1 as our first tier. We're going to have dart 2 as our second tier. These are also going to be hit misses. Probability of a hit is 0.1. That means the probability of a miss, because it's got to add up to 1, is 0.9. Independent events, so the fact that we got a hit first time round isn't going to change the probability. So we're just going to go through, label all the branches exactly the same as the first set of branches. probability of hit equals 0.1, probability of a miss equals 0.9. Working across the branches, remember, across the branches, independent events, if I want probability of a hit and a hit, we're going to get 0.1 times 0.1. I'm only going to write it out the first time, 0.01. So then the probability of a hit and a miss equals 0.09. Probability of a miss and a hit is 0.9 times 0.1, so I get 0.09. And then probability of a miss and a miss is 0.9 times 0.9, which is 0.81. If I add these together, 0.81 plus 0.09 is 0.9, plus 0.9 is 0.99, plus 0.1 is 1.0. So we get there. Okay, so having done all the hard work, having labelled the tree diagram, having done all the end probabilities, what we needed to know is probability that she hits exactly once. So exactly one hit. So where can exactly one hit happen? Well, you can have a hit and a miss, or you can have a miss and a hit. So it's probability miss and a hit, or hit and a miss. It doesn't matter which way around we write these. So I get 0.09 plus 0.09, which equals 0.18. And we're done. Okay, so I hope you understood that question. You now understand how to do tree diagrams. Okay, so we're almost there then, finishing off just slightly with conditional probability. Now, the conditional probability is when the probability of one event is dependent on the outcome of another event. So, for example, the classic question you get in GCSE is if a ball is taken from a set of balls and not replaced. The order of successive events is a key consideration when we use a tree diagram. So we're going to do this using a tree diagram again. It's slightly more complicated, but not massively. There's one extra bit of theory we need to know. So we've got the probability of Billy catching a bus to school is 0.4. If he catches a bus, the probability he's late is 0.2. If he doesn't catch the bus, the probability he's late is 0.5. We want to find the probability that Billy is late to the school. So, first event is probability of catching a bus. Second thing to happen is whether he is late or not. So let's use bus, B for bus and W for walking, and then let's use on the late one L for late and N for not late. Okay, so these are all the things that can happen. Now, probability that Billy catches the bus is 0.4. So the probability that he walks is 0.6. Now this is why the order of the events is important. He must catch the bus. It's a choice of catching the bus before he actually gets to school, and that defines whether he's late or not. It said in the question that if he catches the bus, the probability that he is late is 0.2. Now, that means the probability that he's not late must add up to 1, which is 0.8. Now, in his second set of branches, we can always put like a dotted line down there, it's not the same as the others. The fact that he's walking to school changes the probability of whether he's late or not. Probability of whether he's late is going to be 0.5 if he walks, and so the probability that he's not late is 0.5. So all that changes is that these second tier of branches, the probabilities depend on what way we've picked, gone along through our diagram through these first tier of branches. Probabilities at the end, probability bus late, multiply across the branches. It's exactly the same as we've done before, so 0.08. Probability bus and not late, multiply across the branches, 0.4 times 0.8. It's 0.32. Probability of he walks and he's late. So 0.6 times 0.5, which is 0.3. And probability he walks and he's not late is 0.6 times 0.5 again, so I get 0.3. Add them up, 0.8 plus 0.32 is 0.4, plus 0.3 is 0.7, plus 0.3 is 1. So it looks like I've done these correctly. The question asks, find the probability that Billy is late to school. So probability, he is late. Well, in which situation is Billy late? Here, Billy is late, this top one, and then here, Billy is late. So I've got probability of catching the bus and being late, or probability of walking and being late, which gives us 0.8 plus 0.3, which equals 0.38. The key thing on this is just remembering, how does this first tier of branches affect this probability? So just pay attention, be careful with the question, think about how you're labelling these second set of branches. This is the key consideration, this is the toughest part of GCSE probability, and this is where S1 will pick up from on tree diagrams. So for you to try, a bag contains 5 red balls and 7 blue balls. A ball is taken from the bag and not replaced. This is an important part of it. A second ball is then taken from the bag. We want to find the probability of taking 2 different colours. So at this point, I'm going to draw a tree diagram. Remember what I said in all the information I've given you. I want you now to pause the recording and attempt the question before you proceed. Okay, so let's look at the answer. We had 5 reds, 7 blues. So on each branch we're going to have ball 1 and ball 2. So they're the 2 things, one after the other. We can pick first of all a red and a blue. And again, the second balls we can still pick a red and a blue. Okay, so picking the first ball is easy. Probability of a red equals 5 out of total of 12 balls. Probability of blue is 7 out of a total of 12 balls. Now, the second set of branches is really important. So if I pick a red ball first, what we have to consider is what's left. Well, I'm going to have 1 less red ball, so I'm going to have 4 reds, but I'm going to have the same amount of blue balls. So now, probability of a red is 4 out of 11. Probability of a blue is 7 out of 11. If I pick a blue ball first, then I still have 5 red balls, but I now have 6 blue balls. So my probabilities have changed, so I get probability of a red equals 5 out of 11, and probability of a blue equals 6 out of 11. And this is all that's changed. Just on the second set of branches, I've had to consider how many balls have I got left if I've taken a red first of all. And then I've had to consider how many balls do I have left if I take a blue first of all. The rest of the question is now done exactly the same. Probability of a red and a red. Multiply across the branches, 5 twelfths times 4 elevenths, 20 over 132. Probability of a red, then a blue, is 5 twelfths times 7 elevenths, 35 over 132. 11 times 12, yep. And then probability of a blue and a red is 7 twelfths times 5 elevenths, that's also 35 over 132. And finally, probability of a blue and a blue is 7 twelfths times 6 elevenths, which is 42 over 132. Add up the numerators, so 35 plus 35 is 70, plus 20 is 90, plus 42 is 132. It looks like we've done this correctly. So the question asked, find the probability of picking 2 different. So different. So that means, how can I pick different balls? Well, I can have a red and a blue, or I can have a blue and a red. So I get 35 over 132 plus 35 over 132. which gives me an answer of 70/132. Okay, I hope that all made sense and that you've been able to answer that question and answer any questions that you may have had on it. Okay, so thinking off at this point, now what you need to do is open up the resources that I've given you, have a look at the L1, the Lesson 1 GCSE Essential Knowledge exercise. Make sure you go through that, make sure you cover all the areas and that you're thoroughly confident with all the material inside that exercise. And then if you can complete Assessment 1, so that it is ready and so that you can come along to the first workshop. The first workshop is going to be Friday 15th of January, and you'll find me, Mr. Smith, in L02. It's going to be, let's say, 1:30 to round about 2:15. I'll go through the assessment and you can come in and you can ask me any questions about anything in the exercise and anything in the assessment that you have not understood. Okay, I look forward to seeing you next Friday.